Тихо підуть нам. T. Where are my students? Time to do something. Time to do something. Okay. My table is a bit busy. This for I have this for next lecture. Let's show what it is. It's a fun closed loop control system. We will start with motor, voltage converter, analog to digital converter, and central processor driving this motor with one goal: to keep load voltage unchanged. I can change setting. What voltage do I need? One moment, I will switch second camera. Yeah. Here, voltage and power. Interesting how this thing reacts to net voltage change. 180. I have decreased sorry. I have decreased voltage to 180 volts and power is 40 watts. I can increase voltage up to 200 or here 240 volts, and watch what happens. Control system, two connection, load voltage decreased, load power remained the same. Low voltage same power. High voltage, control system takes an action, and we are back where we was. That's how regulated load works. We see constant power, constant volt amps, load. Voltage, if we have voltage regulation, we have constant power load with constant current. I can increase voltage and see what happens with current. It's a load current. Load, power remain the same. Okay, it's a funny toy, but our today topics is something different. Our today topics is discrete time Fourier transform. First, I would like to show what? I would like to show one element from our previous lectures. I'm speaking on aliasing. Now I have a setup. My signal generator powers supply signal to the scope, you see what digital, it's a digital scope, what digital scope produce. Fine, yellow line. Signal is pure sine with frequency 10 kilohertz. Now I will change what marked as a time base for scope. Really, I will change sampling rate. Watch what happens. I have 10 milliseconds, 20, 40, 100 milliseconds, or 200 milliseconds. Oh, this one is fine. Like this. See what scope's 347. At this moment, we deal with pure sine. What happens? Here on the blue scope, 1 second, I will. You don't see blue scope. 1 second, I will turn my camera. Here, it is blue scope. Kilohertz, pure sine. Watch blue scope. 10 kilohertz, blue sine. I'm changing time scale. In reality, I'm changing the sampling rate. And my scope think that it's a sine with a frequency 3.5 hertz. Here, you see nothing changed. What's going on? Sample, sample. On the next period, sample. That's what happens. Everything. The sampling frequency is too low. Now, more interesting. Here is true form of my signal, 10 kilohertz. I can, for example, I'm adding, what I can add? Here. Now my signal contains, how many? Where am I? 50% of third harmonics. You see? Yeah. Now, watch what happens. If I change sampling rate above Nyquist frequency. Okay, it's around. See what's happened. Compare these two signals. Yeah. What? Wrong frequency. Scope believes what it's 2 Hz signal, and like mirror it. True signal. Maybe 1 second. I will enlarge it. Here is true signal, and here what my numerical scope see, because I'm far right this border of Nyquist frequency. We see effect of aliasing. Sampling frequency is too low. With normal sampling frequency, we should see this 10 kilohertz signal, not 2 Hz signal with some like mirror it. Here, everything as it should be. So be careful with Nyquist frequency. Now, what's now? What's now? Discrete time Fourier transform. I declare today topic as discrete time Fourier transform. Why? What is? What and why? 1 second, I will switch camera. In general, what is Fourier transform? Theory behind Fourier series. If we have periodic signal, I don't know, something like this, which repeats with period T capital. Here m is an integer, so m tend to minus infinity, 0, 1, infinity. We can substitute this periodic repeating signal with a Fourier law or Fourier series. We can substitute the signal, will be C0 by half plus sum, it starts from 1 to infinity, of k cosine double p plus sine wave of double p divided by k. Here we have two factors, C and S, cosine and sine factor. Cosine. And remember this. interesting here? Moment. When we speak in terms of electrotechnics theory, what do we think? What the real, let's say, voltage sine omega t can be represented as a projection of phasor. Rotating with frequency omega. I don't know what some, let's say T1. You know name of this thing? It's a clock. You wait 15 minutes.
15 minutes.
Yeah.
I knew.
What? 50. Yeah, so what I'm talking about. Electrotechnics theory. Electrotechnics theory relies on phasor representation. This is phasor for T1. And this angle will be omega T1. Phasor representation means what? For every voltage or current video width exists its phasor, so a real signal. I don't know. Say this is current with angle phi. In such case, here is phasor representing this current. Short, no. So for every voltage or current with width, somewhere in complex plane, in coordinates +1 or real part plus square root or -1, imaginary part. Now question. First, it's some kind of, maybe, let's imagine, we have max sine omega, say A max sine omega. Real signal, real voltage, real current, real signal. What is the link, where's the bridge between true voltage, true current we can observe, and imaginary phasors on complex plane? What's the connection between them? Connection is Fourier series or Fourier rule. Voltage any can be represented as DC component plus, again, sum starts from 1 to infinity of in our case, what we need for electrotechnics theory, C1S1 would be, this would be real part of our phasor, this would be imaginary part of our phasor. Electrotechnics phasors for ideal sine pure, if we have ideal network from electrotechnics theory. Hello, Music Valley. They are required imaginary part. Only remember, electrotechnics theory operates with effective values. That's why square root from 2 should not be omitted. Because these two corresponds to magnitude, not effective value. Okay. Fourier series give us bridge between real voltage and real current and their representation on phasor plane. That's nice. Now, less pleasant thing. I need to obtain them. I need C and S. Classics, theory of Fourier series, tell me what. Any cosine factor can be obtained as 2 divided. It is for periodic signal. Period. Integrating from 0 to 1. Cosine the time. And sine factor can be obtained, sorry, here should be period. Integrating from 0 to, sorry, here should be T capital. Sine of double P divided by period multiplied by time and integrated is time. These are classical formulas to obtain Fourier factors for Fourier series. Okay, nice. Now we use them. Starting point, I will start with C1. C1, cosine factor or a real part at basic frequency. This will be 2 divided by time. Integrating from 0 to time. My signal, cosine double P divided by time. I'll need this. When God opens the paradise door, you will wait. You will wait even on time when God opens doors of paradise. That's what will happen. Okay, nice formula. You like it? Of course you like it. Why I'm writing this formula? Oh, I have idea about this formula. My original signal, I don't know, maybe it's voltage, maybe it's time. What I need to obtain? Key moment, I need to obtain from 0 to time cosine time theta. I need this integral. In physical meaning, it will be area of some figure. I don't know. I don't know how it will look. For example, maybe something like this. Here's my one period. This white line is cosine omega and blah blah. To obtain Fourier, this magic number, way to Fourier part, I need area of this figure. But there is one tiny moment. Do I have this one? I'm performing processing numerically. I don't have this time, but I have values of my signal. I have sampled values of my signal where I start from 1 and ends, let's say I have n points per period. Here are my samples. Number 1, number n. This is number 2. I'm operating with sample set after analog to digital conversion. So, values of white lines, I don't have them. I only can speak in where they are measured. I have results of analog to digital conversion samples. Let's say red lines are representing sample array for one period of my signal. This will be point n. I need area of this figure. I don't have it. But what can I do? I can connect all my points. Please. I will go attend this meeting. So, you know what I will try to do? I will attempt to substitute area of white figure with some of these rectangles areas. I knew this point, this point, this point, this point, they are measured with analog to digital converter. I have them. Area, let's say this one is number I. Area of this figure is signal value at point I tau multiplied by cosine, cosine. What's the angle for cosine at this point? Double P, yeah? So, this angle is double P divided by number of points. It's correct? Here should be I multiplied by double of P and divided by number of points. You will see in many books. And here is one tiny problem. I started numbering from point 1, but angle at this point is 0. 0. 0. So I need to correct this. Yeah, summation of the rectangles, yeah, is way to obtain numerical integral. So for here, this magnitude, this one is magnitude or height. I also need length. So this is h. L is period divided by number of. Yeah? Area is L by H. Fine. Now I can count all these rectangles together. This will give me with some precision, area of white figure. With some precision, see here, I'm lacking. Till this point, this area will be less than true. At this point, I'm over. I'm above true. As a result, since voltage current appears symmetric, error isn't so high. So, area together, my integral will approximately be what it will be? Double P divided by N. No, stop. Period divided by N. Why double P? Multiplied with sum, where I starts from 1 to number of points in period. Values of my signal, cosine I minus 1, double P divided by here. It's clear how I get this. It's just numerical integration. Now I can write cosine 1 will be 2 divided by n. 2 divided by n. Sum from 1 to number of points. Signal values cosine I minus 1 double P divided by n, pure S1 double n, somewhere starts from 1 to number of measurements per period, sine S1 double P divided by number of points. Here are basic formulas for what? C1, C1. My phasor will be square root C1 square plus S1 square divided by half to obtain y by half to get effective value. F power J arc against S1 C1 with the minus sign because cosine. Here is my phasor for basics. These two sum lays a bridge between result of analog to digital conversion and electrotechnics theory. If I obtain them, I can use all my knowledge in electrotechnics theory to create algorithm of my device. Here is the way to obtain, I knew 3 ways to obtain what is called orthogonal components. To get orthogonal components, so what mean orthogonal components? For your let's say max y cosine sine omega phi, its phasor here, its phasor representation. It should contain a real part and bool imaginary part. To get them, use Fourier series. For any component, if I started, for any component, Ck should be divided by number of samples. Somewhere I start from 1 to number of samples. Original signal cosine K double P divided by period multiplied by I minus 1 and Sk sum from 1 to number of points, signal value, sine K double P divided by period I minus 1, and use Fourier series. Your signal now C0 by half plus sum by K starts from 1 to infinity, Ck cosine K omega t plus Sk sine K omega t. Our interest here is C1S1. First, orthogonal components. Maybe more. It depends on logic, on algorithms you using. But one most used way to obtain orthogonal components, to lay a bridge between true signal in time in form of measurement table and phasors of electrotechnics theory. It was easy part. Now more complex. Name for this stuff is DFT, Discrete Time Fourier Transform. Now question, I have a signal like S max cosine omega 0 time. What should I get as a result of discrete time Fourier transform of the signal? How many frequencies do it contain? 1, omega 0. So I should get something like infinite with thin line at frequency omega 0. This should be something like delta function omega minus omega 0. Yeah? What is delta function? You know? Ideal thin line. Here, spectrum of signal contains only one line. Or two. Or one. One since I draw positive frequency. In theory, there is conjugated at frequency minus omega 0 exists second line in mass representation. Spectral function of any signal is symmetrical. Spectrum function of minus omega is a conjugation of spectral function of positive frequency. But as I wrote, DFT will produce only positive part. Okay. How many frequencies do I have here? Now, here, yellow line. How many frequencies? One frequency, 10 kilohertz. So, its discrete time Fourier transform should yield one single value at a frequency 10 kilohertz. Yes? Where is mass channel 1? What to do? Perform fast Fourier transform. Okay, I will now here. This way. One frequency. Does it look like one single line? No, it's something different. One moment, I will switch cameras. Yellow line is a signal in time. Red line, it's a representation in frequency. It's a result of FFT is optimized algorithm for DFT. Red line is a result of DFT. I'll speed change frequency. Whoa, 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 whoa. What is this? Make it good. A bit better. Good. See, this is good frequency. Okay, it's something like thin line. Anyway, we can see what the maximum is. And this is bad frequency. Good frequency, bad frequency. One more. this is good frequency. We see quite narrow line. And here is example of bad frequency. Large side lobes. I can switch representation at one moment. Okay, good frequency. Bad frequency. I can one thing. One more. Take a look on depends. I will change sampling rate. Some moment it's starting to produce useless thing, but here playing with sampling rate. Where are you? Come back. Hey. Oh, here it is. Bad frequency. Try to catch good one. I will catch you. Closer. Here, near best possible. It's a best possible. I have scope adjusting frequency. Where is my infinity thin line? What your knowledge on Fourier series tell you? Where is my thin line? What's your knowledge? Tells you. Appears you knew answer. Tell me, where is my thin line? Why I'm not seeing ideal thin line? What should be? What happens? And why there are good and bad frequencies? It's a serious question. It's a question of precision of your device. Your, how to say, machinery or your door, your bridge between electrotechnics theory and observed voltage appears not so straight what it should be. So what happens? Why? Nothing is perfect in this world. See what happens if I add third harmonics. And bit of second. Ah. Good frequency. Watch what happened with the in case of bad frequency. Here is signal at a bad frequency. Make it worse. Here. Sampling table shorter and without second harmonic, only with third. With second harmonic. Where is my second harmonic? I can see, I can detect it. On the base of 1, 2, 3, 4 periods, I have sampling table for DFT as 4 periods. Can you tell what this is second harmonic on? It is here. Never invisible. Here is problem on of DFT precision. I'll try to explain. When you obtain orthogonal components with discrete time Fourier transform, one problem waiting for you. There is a wolf in the forest. To switch here. Okay. Let's imagine we have nice ideal signal at 0 time. Let it be as 0 equals S max cosine omega 0 time. Ideal one frequency signal. If we perform real Fourier transform, we will get this as a function of frequency. So, in frequency space, in core, it's a delta function of omega 0. Its spectrum should be one thin line at frequency going up. One should be one infinite thin line at the frequency omega 0. But we don't observe the whole signal. We perform our analog to digital converter for some part of it. Within, we created a table representing some time cut of signal from this point to this point. Here, for example, my cut observation window. I don't have infinite time. I observe my signal from point to point within observation window. So here is some T1, here is some T2. T1 and T2. Yeah? Real signal observed is this red line. Understand what happens? We cut some part of original infinite signal. The red line is what we see. It's our observed signal is 0 when time is T1, S0 from time T1 plus TV, and again 0 when time is greater than T1 plus TV. That's what we are dealing with. We can write it is original multiplied by window function. V from time equals to 0 time is less than T1, 1 T1 time T1 plus observation time, and 0 when time is greater plus T3. When this blue line 0, 1, 0 totally it's my window function. If you remember theory of Fourier series, resulting frequency representation of red signal will be a convolution of my white signal, convolution, and Fourier representation of window function. since Fourier representation of this is delta function, we started from single frequency signal. Here, in my case, results will be delta function omega minus omega 0 convoluted with windowing function. Results will be my windowing function image in a frequency space. So this one, okay. Single frequency signal subjected to Fourier transform, discrete time Fourier transform. Result, this red line is nothing else than a full, sorry, 1 second, here should be, I should be correct, it's offset spectral representation or frequency representation of window function. If you simply cut samples from 2, you can get this one instead of your nice orthogonal components. Now, what about good frequencies and bad frequencies? What's going on? What's a good frequency? What's a bad frequency? Frequency. In theory, we should have this. It's 0 from frequency, actual delta function, omega 0. This is what should be. We got something different. Rough theory. This is magnitude of spectral function. This is convolution of S0. Who writes omega this way? Convoluted with my windowing function. Looks like something like sine of x divided by x. Interesting what this space between zeros is double p divided by TV. If you perform Fourier integral Fourier transform on rectangular window, you will get magnitude of spectral line sine of omega divided by omega. K omega. If you like, I can bring this formula, but it's long. Okay. can show it, what really. So the longer is observation period, the closer this thing will be to. Sorry, change this. Watch what happened. I'm increasing observation window, and you see the central lobe narrows. If in theory I can set this infinite, I will get delta function with only one problem. My device will be infinitely slow. Elongation of observation windows means what? Slow down of my device. I need to wait for multiple periods to get precise measurement. In theory, if for example you do metering where fast reaction to transient isn't required, you need precision. You can buy precision elongating memory. The longer is sample, how to say, buffer, this frame of sampling, the better precision you will get. Yeah? Yeah. But what about limited? So we have n samples. My signal, I will get what? I will get S as a function of I, where I is from 1 to n. I have n samples. For them, in frequency space, I will get what? I will get n points of spectrum. Okay, here k starts from 0, from DC component, and ends with n minus 1. Measurements of original signal are taken with the time space of double P divided by omega station, or 1 divided TD. TD is a 1 divided by sampling rate. It's a space between samples. Fourier, discrete time Fourier transform will be performed for n delta time and delta, or n double P divided by sampling frequency. Space between frequency lines or frequency net delta omega will be double P divided by dV. For our device, it's a measured device, it's a protection device, not important. For our device appears internal frequency scale. Here, 0 DC. Delta omega being double P divided by TV. Its internal frequency scale. In good case, we will see something like this. This is omega 0. If we are lucky, frequency of our process signal corresponds to one of the lines of the frequency net. Wait 1 sec, I will get. Come on. Bit closer. Oh, here it is. It's a moment. I can make it more visible. One moment. Oh, here it is. If we are lucky, we can create such situation. Now, frequency of our signal, we call it 50 Hertz, corresponds to the one of the lines of internal frequency net. In such case, we will see we will see something like this. This one is 4P divided by TV. It's a good case. We can get this. You know what? How? If we need high precision, we can synchronize samples with signal frequency. This will happen if TV corresponds to periods. This will happen if is MT when M is an integer. If you use PLL and get your sampling frequency exactly equals to being exactly integer with net frequency, you will get this. Also, one trick can be done. It's a variable sampling table. You can have 40, 39 or 41 samples per period, for example. You can measure frequency, have one independent channel, net frequency, and according to measurement select number of points per frame. It's when high precision is needed. It can be trick adjustable length of observation window to get end point exactly period. If not luck, what can happen? If you're not luck and omega 0 is between sampling this frequency net lines. What you will get? You will get something like this. Exactly. In worst case, you will see even something like this. Right? With ambiguous result. It's a garbage. It's a worst case. Something like maybe kind of flat. You will get this. So one of the ways to fight it is usage of in such case what signal second harmonic is obscure. Worst case when you have two near frequencies, worst case synchro check relays or something like this. Boom, 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 boom. So what to do? Where to run? Any ideas? Why we are getting this? You seriously making me mad today. Why we are getting not the straight line? Why it's wider? Answer me. Here should be ideal thin line. Why it's not thin? I see, I would say, negligence to my course. Okay. I noted. You will have to learn it. Where is the root of this behavior? We observe limited, how to say, slice or cutoff of our original signal. This deformation is a result of what? Of convolution with window function. In case if we have pure one harmonic, one frequency signal, the thing we observe is nothing else than a spectral or frequency representation of windowing function. If we would like to have less distortion from windowing function, we can manipulate with it. We can use special crafted windowing function with aim to reduce or diminish effects and key where the effect is coming most from the sharp change at the beginning and at the end of window function. if instead of sharp rectangular cut we can use something smoothened effect, distortion effect will be mitigated. Can I push a button? Button, 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 button. Here, I'm activated something called Hamming window. This is rectangular, simple cut from to. And this is something what named Hamming. You see effect. Wait one moment. I will show it. Not set up. Save waveform to reference 1. No. Where is my case white one and now shut up. Feel the difference. Red line, rectangular sampling window, and white line when Hamming, something called Hamming is applied. See difference? See improvement? Especially, I don't have this ambiguous sideline. And what did I activate? Here. Hamming. What is Hamming? Hamming. No. This wait. Something wrong. Where is my Hamming? Yeah. Thing I activated. It's called Hamming window. Its formula 0.54 minus 0.46 cosine of double P I divided by this one. As a result, to understand, I have my side lobes, but this part is determined by side lobes. For simple rectangular window, normalized level of side lobes is at level minus 13 decibels. This is for simple rectangle. It's how to say, it's the best what you can achieve with it's the best what you can achieve. This level is at minus 13 decibels. If you switch to Hamming, this level will be minus 42 decibels. It's very good increase, but not the top. Problem with scamming, it widens top part. If you would like to use this for frequency measurement, you will get problem. You will see decrease in precision. But I have, I don't know, maybe I'm making mistake. 1 second. You know where is my mistake? I should save rectangle as a reference. I should do this. Now white line is for rectangular. Here. I push another button and I have Blackman-Harris observation window. Blackman-Harris will yield, in case of Blackman-Harris window, I will get theoretical minus 92 decibel. This scope cannot realize it. Form Blackman-Harris, where are you? Blackman-Harris, here. Formula for Blackman-Harris window is I hear you. I will not. I will. I should attend. It's okay. It's in 50 minutes. Blackman-Harris 0.35 875 minus 0.48829 cosine of double pi divided by n-1 plus 0.141 28 cosine of 4 pi divided by n-1 and minus 0 1 two zeros 0011 68 cosine of 6 ip divided by n-1. Case formula for Blackman-Harris window. It produces best possible suppression of side lobes, but this area is wider. It is in general, it's not a disaster because it allows small difference between sampling frequency and net frequency. Maybe I have more. What I have? Han. Again, improvement. Han. Gamma. 31 decibel. And spread 4. It's 4 times wider. 4? No, 1.5. It's 1.5 wider than rectangular. So, what's the conclusion? discrete time Fourier transform allows us to obtain orthogonal components. So it's a bridge between sampled measurements of voltage and currents and electrotechnics theory. When we get orthogonal components, we can write our genius algorithms as we are dealing with electrotechnics, objective electrotechnics theory. But discrete time Fourier transform is subject of error caused by limited observation window. To mitigate this, we can or elongate observation time or apply this nice mask for every sample, because we have a sliding window. This will mitigate negative effects of limited observation time. Also, having sample frequency integer multiplied by net frequency reduces this, how to say, fogging or smoothing of central lobe. The closer observation window to integer multiplied by period, then nicer. Not a good. It's having, what can I say? Rectangle or Hamming. I can determine frequency with Blackman-Harris magnitude. Key moment is to suppress side lobes. And one more thing. Nice red line. But this, what should be drawn with over this red line? Our analog preprocessing path characteristic. We can partly correct these white side lobes and all this garbage. See? Periodically appear kind of noises. We can suppress them with flat characteristic of analog preprocessing. This should be taken as one. We can allow, in general, if we are limited in resources or we are balanced, some kind of balanced resource, we can allow one side lobe at the area when we suppressing it with our analog preprocessing part. Good design, real good design, should incorporate meticulous crafting of analog preprocessing part to match characteristic of selected DFT. Okay, I think it's enough for today. Should be, see, difference. And signal, very nice single spectral line. Oops, adding a second harmonic. Oi, 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 oi. Do it to transcend. Okay, second harmonic is a rare thing. Third, here. absolute harmonics. Oi, what do we see? Where is our orthogonal component? Yes, we can improve situation. See how it improves with, if I take more samples, I elongate observation window. But this means what? Slow down of my device. It's not good for protected device. Okay, for measurement. Okay, I have to finish today. I need to, in 5 minutes, I need to attend another meeting. Oops.